Thank you, Chairperson. Good afternoon, everyone. My name is Miyuki and I'm from SOKA University in Japan. First of all, I would like to thank the organizers for inviting me to speak here today. Today, I'm excited to share our recently published paper, Triaxial Accelerometer, based on a semicircular hetero-core fiber-optic sensor. In my talk today, I'll give a little background on tracking vibration. Then I'll discuss prior accelerometer research, and then I will introduce and evaluate the proposed triaxial accelerometer based on a semicircular hetero-core fiber-optic sensor. Tracking vibration in industrial machinery is essential for the early identification of failures. For example, suppose the normal vibration waveform pattern is like this. Abnormalities in industrial equipment can be detected by comparing a vibration pattern with those in actual operation. Measuring changes in vibration amplitude and frequency can detect imbalance, looseness, misalignment, or bearing wear. Next, I will explain the accelerometers that have been proposed for tracking vibration. Electric-based accelerometers include capacitive, piezoelectric, and piezoresistive. These sensors are highly sensitive and widely used. However, they are affected by electromagnetic interference and are dependent on temperature. These issues may output signals in harsh environments affecting diagnostic results. On the other hand, a number of fiber-optic accelerometers has been developed. For example, FBZ, FBI, and hetero-core structure. These fiber-optic accelerometers are robust to EMI and harsh environments and have the advantage of being small, lightweight, no risk to explosion, and resistant to chemical corrosion. In addition to these advantages, for accelerometers based on hetero-core structures, there is no need for temperature compensation, and it is a cost-effective measurement system. Therefore, hetero-core structured fiber-optic sensors are very promising for tracking vibrations. The purpose of my research is to develop a triaxial accelerometer based on a semicircular hetero-core fiber-optic sensor for vibration monitoring. First, a 3x3 sensitivity matrix is calculated using the sensitivity obtained from the frequency response to extend the uniaxial hetero-core fiber-optic accelerometer to a triaxial accelerometer. Second, we evaluated its performance as a triaxial accelerometer when the optical loss obtained from acceleration in 3 directions is converted to acceleration using a 3x3 sensitivity matrix. Next, I will explain the bending sensor based on hetero-core structure. The figure on the left shows a hetero-core structure. The sensor is fabricated by fusion splicing to optical fibers with different core diameters. Light leaks when bending occurs in the small core diameter called the heterocore region. The light leakage of a heterocore optical fiber bending sensor is characterized by this linear increase with bending curvature. Therefore, we tried to apply hetero-core fiber optic to an accelerometer. Now, I will explain the proposed accelerometer based on a semicircular hetero-core fiber optic sensor. An optical fiber containing a heterocore region is fixed to the base at both ends of the optical fiber so that the radius of curvature is 15 millimeter. When vibration is applied to the sensor, the optical fiber beam deflects, causing curvature change in the heterocore region, and optical loss occurs. In this figure, deformation in the y direction is deformation as in plane shear deformation. Deformation in the z axis, z direction as in plane compression deformation, and deformation in the x direction as out of plane bending deformation. This figure shows the three directions of the force displacement characteristics of the uniaxial accelerometer. In all three directions, the optical loss responses have a highly linear sensitivity. We can also see negative sensitivity in the direction of in-plane compression deformation. Next, I will talk about how to convert optical loss to acceleration. To convert optical loss to acceleration, we use this equation. Large O is optical loss, small a is acceleration, and large A is 3x3 sensitivity matrix. The first subscript in the sensitivity matrix indicates the sensitivity axis, and the second subscript indicated the direction of applied acceleration during the sensitivity measurement. There are two conditions under which this sensitivity matrix can be used. The first is that the sensitivity must be linear in the amplitude characteristic. The second is that it can only be used in a frequency range with a stable sensitivity in the frequency response. This slide shows the experimental configuration for the evaluation of triaxial accelerometer characteristic. The three fiber-optic accelerometers are symmetrically arranged in the center of the side of the cubic base. The frequency response is obtained for sensitivity in the frequency range of 10 to 1000 Hz. Amplitude characteristics are obtained from optical loss characteristics at sinusoidal frequencies of 40 Hz and 80 Hz. The left graph shows the frequency characteristics, and the right graph shows the amplitude characteristic. Both show the characteristics of the x-axis sensor. In terms of frequency characteristics, the proposed accelerometer has a stable sensitivity below 19 Hz. In addition, the optical loss of the proposed accelerometer increases linear with acceleration in all excitation directions. The y-axis and z-axis of the proposed accelerometer also showed the same trend. Therefore, from these characteristics of sensitivity matrix applicable to the frequency range below 90 Hz was calculated. The values of the calculated sensitivity matrix are shown here. In order to apply acceleration in three directions, the proposed accelerometer and a reference accelerometer were installed on a shaker at inclination with respect to axis. As shown in the figure here, we defined beta as the angle associated with the rotation of the x-axis, and delta as the angle associated with the rotation of the y-axis. This figure shows an example of the installation when delta is 30 degree and beta is 45 degree. This slide shows real-time responses. The graphs on the left shows a low waveform and compares the case where the acceleration was calculated using only primary axis and the case where the acceleration was corrected using the sensitivity matrix for performance comparison. From top to bottom, the X, Y, and Z axis responses are shown. The sensitivity matrix gives the acceleration closer to the reference sensor values, confirming that it is well corrected. The resultant acceleration in the three axial directions when varying delta and beta is the error relative to the reference accelerometer. The highest error calculated from primary axis sensitivity is 20.2%. Whereas the largest error corrected by the 3x3 sensitivity matrix was 6.97%. The use of 3x3 sensitivity matrix shows improved accuracy. In conclusion, we proposed a triaxial accelerometer based on a semicircular hetero-core fiber-optic sensor for vibration monitoring. The proposed accelerometer has stable sensitivity below 90 Hz and linear optical loss characteristics with respect to acceleration. More accurate acceleration measurements can be made by correcting using a sensitivity matrix. That's all for my presentation. Thank you for listening.